Muy buenos días a todos y bienvenidos a Charlas con Energía, Confiabilidad mediante analítica y programas de análisis de gases disueltos para empresas eléctricas. Vamos a dar un espacio de 5 minutos para iniciar y a las 10:05 comenzaremos ya el evento. Charlas con Energía, Confiabilidad mediante analítica.
Bueno, muy buenos días a todos. Bienvenidos a este espacio de Charlas con Energía, que es un espacio que consideramos importante para compartir los temas que son de interés para las empresas del sector energético y del sector eléctrico. Hoy tenemos la conferencia de Confiabilidad mediante analítica y programas de análisis de gases disueltos para empresas eléctricas, impartida por Zach Draper, que es científico de la empresa Delta X Research. Bienvenido, Zach. Entonces, pues, está también el equipo de PTI acompañándolo. No sé si quiere intervenir primero Juan Jorge o Zach. Empiezas de una vez. Welcome, Zach, and go on.
Thanks. Let me just share my screen here.
Solo un pequeño comentario mientras que Zach comparte su pantalla. Si requiere alguien la presentación va a ser en inglés, entonces si alguien requiere alguna pregunta, si alguien requiere alguna clarificación en español, por favor nos dejan saber y nosotros procedemos con ella. Un buen día para todos y muchas gracias por acompañarnos.
Okay, thank you for everyone for coming. So first off, I just want to say that that there's a lot of jargon that goes around in the industry, and it's important. And people say these things a lot to just in order to sound smart, including myself. But it's important that we ask the tough questions about what people actually mean by these things, in order to understand how they're constructed, what they mean, and how they're actually going to impact your day-to-day operations. Because otherwise, they're just a theoretical exercise.
You can continue, Zach.
Okay. So some of the potential benefits that are promised by sort of going to a digital asset management system is sort of to increase reliability, reduce potential failures, increase safety, and just have sort of a general awareness of what the status of your fleet is so that you can make decisions about what to replace, what to prioritize for maintenance, and that sort of thing. And sometimes we come up short on this, but this is sort of the guiding principle of where we're trying to go. And so what we're always trying to shoot for. But what does it actually really mean? Well, for most people, it means just a lot of data that they're getting flooded with all the time. And it's a matter of trying to figure out how to figure out the most useful things about the data in order to inform you about what you should be doing. So you want to end up collecting a lot of data from your assets in order to learn things about those assets that you can then apply. So if you can create a model for understanding how the transformer is operating, you can make predictions about whether that asset needs maintenance or whether or not that particular asset is at risk of some kind of failure in the near future. So in this presentation, we'll be talking a bit about reliability-based DGA, which is a model that we've created by collecting a lot of data on transformers through dissolved gas analysis and failure data, and being able to correlate the dissolved gas analysis with failure data allows us to get a more objective understanding of what the risk involved is in continuing to operate a transformer that is producing a lot of fault gas. This is a slide a bit about us, about Delta X Research, about myself and our other principal scientist, Jim DeCarm. It's something that our marketing department insists on, and it makes us sound more important than we actually are. So I'll just point out the fact that neither of us are electrical engineers. and that comes with pros and cons. The pro is we understand data and how to manage it and analyze it for advanced analytics. The downside is we've never been held responsible for an actual transformer. So always take that with a grain of salt, and you're going to get pluses and minuses for whoever is at the table trying to make decisions about a transformer. So what is DGA? Dissolved gas analysis is a sort of widely used screening test for electrical assets. It's basically gases that are produced when the insulation system, either the oil or the paper, is breaking down. It allows us to have some way of assessing whether or not something is going wrong with a transformer or LTC or bushing or whatever it happens to be. But the question is often, okay, we see these gases, but what do they mean? How severe is the problem? What exactly is the problem? Is it something that I need to address right away? Or is it something that I can wait 6 months or a year from now to do maintenance later on it? Collecting data can come from a lot of different parts of the transformer. And what most people do is they collect this data and compare it against some kind of standard, whether it's IEEE or IEC. They'll have some sort of guidelines about what certain values that you measure should be, or certain thresholds. And so that's sort of the first level approach. But what we really want to get towards is being able to analyze a bunch of data and cross-correlate things like dissolved gas and reliability data to get an objective view of, you know, how reliable is a transformer given a certain level of gassing. There's many possible components to monitor. The three main ones in a transformer are the windings, LTC, and the bushings, all of which can be sort of assessed with DGA to varying degrees, depending on the type of bushing or the type of LTC. But being able to sort of tackle those three main failure modes is important in order to increase the reliability of operating a transformer. So an example in conventional DGA, or what I refer to as conventional DGA, is you take gas measurements from the lab and you compare them against guidelines like IEEE or IEC. And those guidelines were established by basically saying, take a large database of gas values and figure out what the 90th percentiles are on that database of gas values. So it tells you how unusual a particular measurement is, but it doesn't give you a sort of a precise understanding of what the risk involved is in seeing that level of gas or that rate of change in gas. And that's really where you need to bring in other data sets like reliability data and cross-correlate it with the dissolved gas analysis. And it can also be challenging too, because there's multiple data sets and multiple people involved. Transformers live for, can live for quite a long time. So you need to collect a whole history of information to really get a good understanding of the transformer. So what can we do beyond the conventional besides just comparing a single data set and saying whether or not this data is unusual or not? Well, there's sort of two sort of main approaches. So there's, you can have a sort of a top-down approach where you basically say, I have a problem, I need transformers to be functional, and I need to know when I need to replace them. So you start with that problem and you make the data kind of fit that, that problem so that you can get an answer to it, but it's not necessarily something that you can answer from the data. You're just making the data fit into the problem that you're trying to solve. On the other hand, you can do a bottom-up approach where you look at the data and you see what does the data actually tell you. Does DGA correlate with the reliability or not? It may be that you're measuring something that has no relationship to whether or not the transformer is serviceable or not. And the only way you understand that is by actually looking at the data instead of trying to impose the idea or some assumption that this data set is going to tell you something about the problem that you're trying to solve. The downside with the bottom-up approach too is that you may spend a lot of time searching through the data to try to find something useful, and you may come up with nothing. So you may not end up solving the problem that you tried to set out to solve. So here's just sort of a list underscoring that, that starting with a problem, it's good for a grounded real world truth, to be able to it's easy to comprehend. It's easy for people who need to make decisions to understand if, like, okay, we're trying to solve this problem, we need to increase reliability. The problem is that a lot of assumptions get folded into it. And then you potentially miss out on some key insights that are in the data that would otherwise get ignored because you're making all these assumptions in order to try to solve a problem and make whatever data set you have fit that problem. Starting with data, you really try to learn from the data. Let the data tell you what there is to say about it. And you may be surprised and hopefully do so in a way that doesn't allow assumptions that maybe came from 30 years ago to influence how you're understanding the data today. Then, of course, the downside is it's a lot of time involved in research. You often can get things that are confusing to people who have to make decisions. And so it's a matter of trying to understand and make it in sort of a digestible way of what the data is actually saying. And ultimately, there's no one or right way in this. It's often something that has to be sort of balanced between figuring out what the problems are that actually need to be solved and seeing what the data can actually tell you about those problems. So for an example, what we'll talk about is how DGA has been interpreted. So one of the things that we found is that there's some inconsistencies in the assessment. So DGA is sort of a three-step process where you're identifying, is there a fault in the transformer or not? And if there is a fault, how severe is that problem? Figuring out that has been sort of a gap in our understanding in the DGA process. Fault identification is fairly reliable. If you use Duval triangles, they're pretty dependable. And as long as you're using, incremental gas values on clearly identifiable faults and not just on noise values, then it's fairly dependable. So what we really wanted to focus on was sort of this risk assessment in reliability-based DGA. So one of the first things we did was to try to simplify the problem. And one of the things is that the gases are not what going to cause the transformer to fail. It's the fault which is generating the gases that is going to cause the transformer to fail. So whether it's a weak spot in the transformer windings, burning paper, or if it's a loose tap connection, those kind of things are what's going to fail the transformer, and the gases are just sort of a symptom of the problem. So in order to get at the root cause and to simplify the data, we start looking at what's called a normalized energy intensity. So we weight the gases by how much energy it actually takes to form those molecules from the insulation system, whether it's the oil or the cellulose in the paper. And then that gives us sort of a one-line diagram to assess when the transformer is gassing and by how much. Then we sort of built a reliability model from it by using sort of standard reliability statistics, where we measured the fault energy index for transformers that are operating in service and transformers that failed in service, in order to understand what the risk involved is for that particular amount of gassing. And some of the things that we derived from that was a cumulative severity, which is an estimate on how lucky you got to where you're at today. So it's the fraction of transformers that would have failed had they had a similar level of gassing. And then we have the hazard factor, which is a forward projection in risk, where we look at the current gassing rate and we say, and we look at what the current failure rate is in the model in order to determine what the risk is going into the next year. And then that can help you prioritize maintenance for things that are gassing in a very risky way versus transformers that are not gassing at all and appear to not have any risk of failure. So the question is, how do you get from just gas values and data to an actual model that can tell you something useful that will actually impact how you do your day-to-day operations in prioritizing maintenance and replacing assets and that kind of thing? So the key to that is data management, because you're taking data sets from multiple different places and trying to bring them together to figure out the relationships and how those are related. Regardless of the kind of approach, you have to sort of establish key identifiers. You have to be able to understand the assets in your fleet and be able to track all the different data streams that are related to an individual asset. You also want to minimize the data travel distances. So every time data goes from one system to another, you have to translate that data. And that opens up an area for potential corruption of that data. And so you want to minimize the amount of travel distance of that data so that you have a clear understanding of what the data is and how it goes cleanly into some kind of analysis engine, which is going to give you some results. And oftentimes there's no one system that rules them all and understands everything very well. So oftentimes you'll have systems that are experts in a particular data set and they just have to work well with other systems. And it's also useful to determine a system of record so that that one program is sort of the key program or system of record for a particular data set. And then finally, taking advantage of the cloud is really important because it allows you to push updates in your analysis very quickly and allows you to bring data sets together quickly. So determining key identifiers, I mean, this is a really critical step. If you don't do this step, then you might as well forget about trying to do advanced analytics on your assets. You know, if you think about it, the government tracks you by some kind of tax number, and then they assess your tax based on that number, right? They have to track you in some way so that it's consistent. And the same thing applies for assets in a utilities fleet. So serial numbers work most of the time if you're on a small fleet, but not all the time. There might be conflicts in the numbers. So usually you have to assign a unique equipment number to all of the assets. And one of the things you never want to do is use the designation or the pad number for a transformer, because that's like using your address for your medical records. If you ever moved positions, well, now your medical records are not going to follow you because it's based on your address. That's why you really need a unique identifier that's tagged to that asset itself. And you also really want to identify down to all the subcomponents of that asset. So, so the equipment number overall, the apparatus type that you're focused on, and the individual tank when you're looking at DGA data. Because the gas values that you're measuring come from some oil compartment, and so you want to be able to identify down to that compartment. Okay, so on minimizing data travel, again, what happens is whenever you have multiple systems involved, it can become like a kid's game of telephone where they're passing a message around in a circle, and by the time it comes back to you, the message has been corrupted. So you really want to minimize the number of systems involved, such that you have your one system of record for, say, nameplate data. That one system sends that nameplate data to all the other systems that require it, and you minimize the number of places where that data is jumping from one system to another. The reality is some software developer is going to have to figure out how to translate the two systems together, and they're not necessarily experts in transformers. So they're not maybe the best educated in what the data actually means, and they're just trying to make things fit. And then you lead to more translation errors the more systems you go through. And at the end of the day, the analysis results that you're going to be basing maintenance decisions on are going to be corrupted if that data is corrupted along that path. And so it's also why it's crucial to use sort of key identifiers in order to track that data as it migrates from one system to another. So also, one system can't sort of rule them all. There's a lot of promise in machine learning and general artificial intelligence. But the reality is you really have to build an ecosystem of software. And that ecosystem involves software that's an expert in a particular data set. And they have to communicate well with each other so that you can bring all of the data together when you're making your decisions. And machine learning tools are very useful, but they're even more useful when you have some kind of human expert helping to guide that analysis, so that you're not just sort of spinning and correlating variables that have nothing to do with each other. And one day there will be general artificial intelligence, and we can all take a vacation because the general AI will just make all the decisions for us, but we're not there yet. So determining a system of record is important for when you're understanding sort of particular data sets and what's good for a particular data set. There may be a software program that's really good at tracking nameplate data. One might be good at DGA data. Another one might be really good at power factor testing. And all of those systems will have to communicate with each other. But it's important to establish one of those systems as being the system of record for a particular data set. So for like nameplate data is a common one that has to be shared amongst a lot of different systems. So establishing one system where anytime you update an asset, add a new transformer to the fleet, or take one out of service, there's one system where you need to go update that, and then that system will propagate all the nameplate data throughout the system. And sometimes certain systems will need to know what the KV rating is, other systems won't. but there needs to be one sort of system of record that has all of the data that you know about that particular data set, and it's sharing amongst the other systems. And then maybe there's local copies of that data on those other systems, so that the systems are not dependent upon one another, but the system of record is the one that's going to be sort of the judge of whether or not that data is accurate or not. And it's the one that's sort of aggregating that kind of data and disseminating it to the other software systems in the ecosystem. The other thing is to really take advantage of the cloud. This sort of comes into conflict with the electrical utility industry a lot because they're really focused on cybersecurity, which is important. And the crux of it is that the cloud, the advantages of the cloud are very important to sort of this kind of idea of asset management, such that we need to sort of address the cybersecurity concerns head on, and just say that cloud computing is important because it allows us to make mass updates to the analysis quickly. It's able to easily share data with other systems. There's redundancies and backups. So if a particular server crashes, there's backups to take over for it. And the downside of the cloud is that there are more gaps where hackers could potentially try to get into the system. But as long as it's done very carefully, we can overcome these hurdles. So using data management, we can build these kind of models. For dissolved gas analysis, when we were understanding reliability-based DGA, we really wanted to correlate the gases with actual failure data. We didn't want to use the traditional assumption that the 90th percentile tells us what's risky or what's not risky. We wanted to actually look at what the failure data was telling us about the risk involved in that gassing. So what that required is tracking all the failures, and it's not that common of a practice in the industry as much as it should be. But by collecting all of those failures, we had something useful to go on. And you can filter sort of the failures that are predictable versus not predictable. So for example, if a raccoon gets inside a bushing and fails a transformer, that's not something that's predictable by dissolved gas analysis, right? So in some cases, it's not useful for predicting failure. But it's important to still collect all of that information so that we understand what failure looks like. And then we can figure out how that relates to dissolved gas analysis. And for us, really, failure is anything when the transformer is unexpectedly taken out of service, when it can't deliver power. And collecting all of that failure data, it may not seem useful in the present, but it's going to be very useful down the road when you're trying to understand what the most common elements of failure are. And it allows you to correlate failure data with other data sets. So you should really try to track everything you can from failure and never delete it, save it. And down the road, you may come up with some brilliant idea that allows you to predict failure that's impending. So in our research on dissolved gas analysis, we sort of simplified the gas data into the fault energy indices, sort of tracking how much energy is being dumped into the insulation system, whether it's the oil or the paper. And then we use that historical trending of gassing to associate it with the failure data so that we can understand in an objective way how gassing relates to failure. So the way we did this is we took failure data from two different utilities, source A and source B. They have different fleets, different maintenance policies. But we looked at what sort of the survival probability was as a function of that NEIHC. So we're measuring NEIHC for the entire fleet and the failure cases to understand how that gassing relates to failure. And what was noticed sort of early on was that despite these being two different utilities, the survival probability curves lined up pretty well. And in fact, they were statistically indistinguishable. So you can see some error bars on here. And so what that meant is we essentially combined those two data sets to create a single model. And then basically every stair step in the Kaplan-Meier curve there is another transformer that's failing. And we fit sort of a smooth model to this curve in order to create a model that we can use for all transformers. So basically we can measure what the NEIHC is for any given transformer and then compare it against this curve to see what we expect its survival probability to be. And one of the useful things that comes out of that kind of model, so this is all based on essentially really like textbook reliability statistics, is you get what's called a failure rate or a hazard rate. And that sort of tells you sort of in the near term how risky is this observation that you're seeing. So we're observing the fault energy index and we're determining how risky that is. And what's sort of interesting about this model is that if you looked at the typical standards that say high gas values represent higher risk, that's sort of the implicit assumption that they make. It turns out that that's not actually true, that the failure rate starts to decline with the more gassing that you do. And that's only something that you learn by a bottom-up approach, by looking at the data and saying, what does the data actually tell me, rather than imposing some assumptions from the top down. Right, so we're trying to collect all this data. There's multiple data streams coming in. The key is that we have to sort of identify sort of the key problems that exist and how that's going to actually impact people on the ground and how they're making decisions. And so what we need to do is sort of accurately determine what the risk involved is in operating those assets. A lot of people want to move to sort of a condition-based maintenance strategy. The reality is that condition-based maintenance is only a small subset of testing is actually based on the condition. So if you're actually doing electrical testing, power factor testing, that's sort of the condition of the transformer. But it's very expensive to do and it requires de-energizing a transformer. So we want to eventually determine the condition of the transformer. But what we're often left with is using statistics to determine what the risk involved in operating that transformer is. So an example of how we sort of use this model in reliability-based DGA is, so we have this accumulated NEI. So this is our observable in the gases. We have the model, we compare that, we measure it for an individual transformer and then compare it against this model. And it gives us these kind of statistics where, you know, the cumulative severity is 4.5%. So that means 4.5% of transformers would have failed had they had a similar level of gassing up to the present day. And then we can project into the future and say, okay, if it keeps gassing at the current rate, how much more risk am I adding to that transformer within the next year? And that's that red arrow there showing the hazard factor of an additional 4%. And if you think about the background failure rate of transformers is something on the order of 0.5% to 1% per year. then this is essentially sort of 4 to 8 times that. So this would be a very risky transformer to be operating, and it really necessitates some kind of other intervention. So taking it offline, doing some power factor testing, figuring out why it's gassing. So it doesn't tell you sort of exactly what to do, but it tells you a general sense of risk involved in operating that transformer, and allows you to prioritize the risky transformers over the less risky transformers. So that brings me to another point about symptom versus condition. So dissolved gas analysis is not really a condition of the transformer. It's a symptom of that transformer. So for example, if you have a headache, your headache could either mean that you are dehydrated, or it could mean you have a brain tumor. Both of those things could be true for the one symptom of just having a headache. And so often symptoms are just sort of signs or evidence or clues about what the condition is, but you really have to build a lot of context around those symptoms to understand what the risk is. Whereas a condition is something that you can physically measure, right? So, you know, you can measure what the power factor is in a transformer, and that tells you how well that transformer is insulating when it's under load, right? So that is an actual conditional measurement, and something you can use to make sort of rigid decisions on. You know, a condition is something that, whether it's true or not, can tell you this transformer is serviceable or this transformer is not serviceable. The problem is it can be very difficult and time consuming to measure those kind of things. So we're often left with collecting a lot of different symptoms and trying to understand the symptoms rather than trying to understand the condition of the transformer. So for example, in transformers, you might have a transformer that's been gassing in carbon oxides for 12 years. But there's lots of different mechanisms for that. So you could either have a transformer that's overheating due to load, maybe the cooling system is not working adequately, or maybe you have winding paper that's burning a hole through the paper insulation. So either all of those things could be true based on this sort of one symptom. And so what you really have to do is use the symptom to understand what the risk involved is, and then use actual condition-based measurements to make sort of solid decisions on. So just to summarize the advantages and disadvantages here, is a symptom-based maintenance or maintenance strategy it's low cost, non-invasive to measure. So you're not taking this asset out of service. The problem is that it's hard to interpret. Whereas on the condition-based side, it can be expensive and invasive to measure, but it gives you more definitive answers about that asset. So really you have to do both strategies in parallel, where the symptom-based strategy is going to optimize how you apply your condition-based maintenance strategy. So if you can identify particularly risky assets, then you can use condition-based measurements on those risky assets and save your money on the assets that are not showing any signs or symptoms of potential failure. Right, so a symptom analysis is important because of its utility and being low cost and non-invasive. And it allows the prioritization of condition-based maintenance. So it's basically your high-level radar system to make you aware of your fleet as a whole. And then you can use that symptomatic-based maintenance to prioritize based on risk. And then the condition-based maintenance will tell you more concrete about whether or not the transformer is serviceable or not. And it's really important to not confuse those two systems. So you don't want to use sort of dissolved gas analysis as your primary mechanism for determining serviceability in a transformer, because it's a symptom of the problem and not a condition of the transformer. So in an example like this, you have your symptom-based metric, which is telling you this transformer is very risky. And that gives you some good insights into how risky and what the problem might be by actually correlating failure data with the gassing data. And so it can be still very useful, but you have to understand what it is you're actually doing, what kind of analysis is being correlated here. So in conclusion, data is extremely valuable, but it's only valuable if you manage the data well. Otherwise, you're going to be lost and spinning in a mess of data. And there's lots of monitors and sensoring systems out there, but if you're not bringing that data together and leveraging it to make decisions, then you honestly might as well not be investing in all that technology. And really, to manage assets effectively, you really need to track failure data. So you really need to understand how the data that you're measuring correlates to the risk of failure. And that really requires you to track as much data as you can when failures occur. Right? I mean, it's sort of a classic that we often learn from failure. And the greatest mistake you can make is to not learn from failure. And a symptom-based analysis and maintenance strategy is very helpful in order for you to guide your condition-based maintenance strategy. And with that, thank you for listening.
Zach, there's a couple of questions.
Okay.
One question is, what is your opinion regarding the performance of online gas monitors?
Well, that's a really great question, and I probably could spend an hour just talking about that. I think they're potentially useful for understanding failures that may occur on short time scales and sort of being able to predict those kind of failures. The problem is that there's all these data management issues that affect them. So oftentimes you'll have monitors hooked up that are not actually feeding data into a central system to be analyzed effectively. You have monitors that are producing spurious values. You have other monitors that are not really installed correctly, so they're measuring gas that's not really representative of the whole volume of the transformer. There's a lot of different issues with them. I think it's there's good justification for having them on assets that are really critical. If you need to know and be forewarned that a failure is going to occur on a particular asset, within the weeks to months time scale, then a DGA monitor is a good idea to have. Because otherwise, typically you're doing lab sampling, which is on a yearly time scale. So you're kind of flying blind when in between that sampling interval. So they can be useful. It's just important to get the execution right, I think. Yeah.
Thank you, Zach. There's another question. What do you think about the new IEEE C57-104 2019?
Okay, these are all great questions. And again, I could have another hour-long presentation about it. I think it's there are some good ideas in it. It tries to address some certain issues like the O2N2 ratio. So we know that the breathing type of the transformer can have a big impact on the gas values. So it's good that it's trying to address that. I think it's sort of in the same paradigm as we were before. It's saying high gas values represent worse condition. I'm going to just take a large database of samples and figure out what an unusual sample would look like. But that doesn't really correlate with actual reliability or failure data. And, you know, I think the people on the committee would fairly admit that they didn't really have a really population analysis to understand, okay, these gas values come from assets that are about to fail, and these gas values come from assets that are operating just fine, right? They didn't have the data to do that when they established the standard. So I think there's some useful ideas in there, including looking at rates of change. There's more emphasis on looking at rates of change, and I think that's useful. But I think there's some problems in sort of the execution and really actually understanding what the risk involved in gassing is. They're sort of just making sort of basic assumptions that we've been making for decades.
And we have another question. Will symptom analysis work in a prediction model, like the percentage of a prediction model? Mm-hmm. What's the best real percentage of prediction for a good model to build?
So like a good model in a symptom-based analysis is really taking a lot of the data that you can and correlating it to whatever thing you're trying to answer. So for dissolved gas analysis, we're trying to answer reliability. Is the asset going to fail or not? And do I need to pay attention to this asset, or can I ignore it for another year? So as long as your symptoms are correlated with that and you're trying to understand that, it's sort of your first level approach at understanding, do I need to pay attention to this asset or not? I mean, you could think of it like a doctor, right? I mean, you go into your doctor, he looks at your symptoms and then makes some decision about, okay, we should send you to the hospital, or I can send you home with some aspirin, right? So it's sort of your way of triaging what assets you need to investigate more versus letting go and for another year. So so any data that you can collect to determine the priority level of the assets is good for a symptom-based approach. And if you need to make a concrete decision about whether or not a transformer is serviceable or not, that's where you need to bring in condition-based assessment and do some kind of power factor testing or something that's actually physically measuring something about the transformer.
Thank you, Zach. Those are all the questions we got so far.
Okay.
Bueno, al parecer no hay más preguntas. No sé si hay algún comentario adicional, un comentario final, Juan Jorge, o alguien del equipo de PTI.
No, Carlos, no, agradecer a todos los que nos han acompañado y a Zach y todo el equipo de DeltaX. Y bueno, estamos listos para atender cualquier otro tipo de inquietud en el futuro.
Igualmente desde la Cámara, muchas gracias a todos por la asistencia, muchas gracias a todo el equipo de PTI, Zach, thank you very much por esta conferencia excelente y pues hasta una próxima oportunidad. Muchas gracias a todos.
Thank you, Zach.
Thanks.